Hello students, welcome back to a new series of mathematics program for grade 9. In this video, we're going to talk about the chapter on vectors and translation. Well friends, today's session is the second part regarding this chapter which will be presented by myself, Mr. Dharamveer Vansi. So let's start. In this program, you're going to learn how to find the magnitude of a vector. What is meant by equal and negative vectors? Students, recall a vector is a quantity having both magnitude and direction. In the first video, we focused on the direction, and now it's time to learn about the magnitude of a vector. Consider the vector AB expressed in column form with components 3 and 4. Now, if this vector is drawn on a grid, we have a directed line segment with starting point A and end point B. Also, the horizontal component, which refers to the horizontal movement from the starting point, is 3 units to the right. And the vertical component, which refers to the vertical movement, is 4 units upwards. Students, the magnitude of the vector AB written as modulus of AB means the length of the directed line segment AB. Let us look again at the vector AB on the grid. The angle between the horizontal and vertical components is 90 degrees or a right angle. Now, if we take the horizontal component, the vertical component, together with the directed line segment AB, we have a right angled triangle with AB opposite the right angle, which means AB is the hypotenuse of this right angled triangle. That is, AB is the longest side. Now, since we have a right angled triangle, we can use the Pythagoras theorem, which states the hypotenuse square, that is AB square, is equal to 3 square plus 4 square. So we have AB square is equal to 9 plus 16, which means AB square is equal to 25. Now to obtain AB, we can use the square root property. So we have AB is equal to square root of 25 instead of positive or negative square root of 25, as length cannot be negative. So therefore, AB is equal to 5 units. Hence, the magnitude of the vector AB is equal to 5 units. Students, in general, for any vector A with horizontal component x and vertical component y, the magnitude of vector A is found using the formula modulus of A, or magnitude of A, is equal to square root of x squared plus y squared. Remember, this formula is obtained from the Pythagoras theorem. Also, the magnitude of a vector cannot be negative. Students, remember also that x and y can take positive or negative values. So, it is advisable when substituting values of x and y into the formula to use brackets in order to find the magnitude of the vector correctly. The following example demonstrates how to find magnitude of a vector. Find the magnitude of each of the following vectors. In the first part, we are given the vector AB with components 6 and 8. Using the formula for magnitude, we have the modulus of AB, or magnitude of AB, is equal to square root of 6 square plus 8 square. Recall, A square means A times A. So here we have square root of 6 times 6 plus 8 times 8, which is square root of 36 plus 64. So we have square root of 100. Therefore, the magnitude of the vector AB is equal to 10 units. In the second part, the magnitude of the vector p is equal to square root of 4 square plus negative 3 square. Now remember, when two negative numbers are multiplied, we obtain a positive number. So negative 3 square, which means negative 3 times negative 3, is equal to positive 9. So we have square root of 16 plus 9, which is square root of 25. Therefore, the magnitude of the vector p is equal to 5 units. In the last part, the magnitude of the vector q is equal to square root of negative 5 square plus negative 12 square. We have square root of 25 plus 144, which is square root of 169. Therefore, the magnitude of the vector q is equal to 13 units. In the next example, the vector r is defined by components negative 24 and k. Given that the magnitude of the vector r is equal to 25 units, find the possible values of k. So we start by using the formula for magnitude. We obtain the magnitude of r is equal to square root of negative 24 square plus k square. Now here we are given the magnitude of r is equal to 25. So we can state square root of negative 24 square plus k square is equal to 25. Squaring on both sides, we have negative 24 square plus k square is equal to 25 square, which leads to 576 plus k square is equal to 625. Now we can eliminate the 576 from the left-hand side by using its additive inverse on both sides, which is negative 576. So we obtain k square is equal to 49. Now, using the square root property, we have k is equal to positive or negative square root of 49. Therefore, the possible values of k are positive or negative 7. Students, now you are going to learn about equal vectors. Two vectors are equal if they have the same magnitude and are in the same direction. Consider two vectors AB and CD drawn on a grid. Let us first express AB in column form by considering the horizontal movement from the starting point A, which is 3 units to the right. So we put 3 in the first row of the column vector AB. Now we look at the vertical movement, which is 4 units upwards. So we write 4 in the second row. Next, we express CD in column form by first considering the horizontal movement from the starting point C, which is 3 units to the right. So we put 3 in the first row. Now we look at the vertical movement. Here it is 4 units upwards, so we write 4 in the second row. Students, observe the vectors AB and CD are represented by the same column vector. So it's obvious that the magnitude of the vector AB is equal to the magnitude of the vector CD, which is square root of 3 square plus 4 square, that is square root of 25, leading to 5 units. So the magnitude of the vector AB is equal to 5 units and the magnitude of the vector CD is equal to 5 units. Therefore, the vectors AB and CD are equal vectors. Students, in other words, two vectors are equal if they are represented by the same column vector. In the next example, we are going to look at how to identify that two vectors are equal. Determine whether the following pairs of vectors are equal. In the part A, we have the vectors DE and FG. So first we express DE in column form by considering the horizontal movement from the starting point D, which is 2 units to the left. So we put -2 in the first row. Next, we look at the vertical movement, which is 3 units upwards. So we write 3 in the second row. Now we write FG in column form by first considering the horizontal movement from the starting point F. Here it is 2 units to the left, so we write -2 in the first row. Now we look at the vertical movement, which is 3 units upwards, so we write 3 in the second row. Observe that the vectors DE and FG are represented by the same column vector. Therefore, the vectors DE and FG are equal vectors. In part B, first we express the vector A in column form. Note here that there is no horizontal movement from the starting point, so we write 0 in the first row. Next, we look at the vertical movement, which is 4 units upwards. So we put 4 in the second row. Now, let us write B in column form. Here again, there is no horizontal movement. So we are going to write 0 in the first row. Now we look at the vertical movement, which is 3 units upwards. So we write 3 in the second row. Here, observe that the vectors A and B are not represented by the same column vector. Therefore, A and B are not equal vectors. Students, now you're going to learn about negative vectors. Consider a directed line segment with starting point A and end point B drawn on a grid. Let us express AB in column form by first considering the horizontal movement from the starting point A, which is 2 units to the right. So we put 2 in the first row. Next, we look at the vertical movement, which is 4 units upwards. So we write 4 in the second row. Now suppose this directed line segment is reversed such that B becomes the starting point and A becomes the end point. If we express BA in column form by first considering the horizontal movement from the starting point B, here it is 2 units to the left. So we write -2 in the first row. Then we look at the vertical movement, which is 4 units downwards. So here we write -4 in the second row. So we've expressed the vector BA in column form with components -2 and -4. Now these components can be written as -1 times 2 and -1 times 4. Students, recall the chapter on matrices, where multiplying a matrix by a scalar quantity implies multiplying each element of the matrix by the scalar quantity. Here, the scalar quantity is -1. So we can write the vector BA as negative of the vector with components 2 and 4. So it is equal to negative of the vector AB. Thus, the vector BA is the negative of vector AB. Students, let us look again at the vectors AB and BA on the grids. The magnitude of the vector AB is square root of 2 square plus 4 square, which is square root of 20. Now the magnitude of the vector BA is equal to square root of negative 2 square plus negative 4 square, which is equal to square root of 20. Therefore, the magnitude of the vector AB is equal to the magnitude of the vector BA. Note, a negative vector has same magnitude but opposite direction. Thus, if we have a vector P, then the vector having the same magnitude but opposite direction is definitely negative P. Students, the following example deals with negative vectors. In the following diagram, in part A, write the vectors P and Q in column form. In part B, show that P and Q are negative vectors. So let us start by expressing P in column form, by first considering the horizontal movement from the starting point, which is 3 units to the left. So we write negative 3 in the first row. Next, we look at the vertical movement, which is 2 units upwards. So we write 2 in the second row. Now we express the vector Q in column form by considering the horizontal movement from the starting point, which is 3 units to the right. So we put 3 in the first row. Next, we look at the vertical movement, which is 2 units downwards. So we write negative 2 in the second row. Now, in part B, to show that the vectors P and Q are negative vectors, either we show P is equal to negative Q, or we show Q is equal to negative P. Here, we start by P expressed in column form with components negative 3 and 2. Now, these components can be written as negative 1 times 3 and negative 1 times negative 2. So, P can be written as negative of the vector with components 3 and negative 2. Therefore, P is equal to negative Q. So, P and Q are negative vectors. Students, now it's time to take some exercises for practice, which will help you to understand better today's lesson. So take note. The question number 1. Next, the question 2 and question 3. To summarize, in this program, you have learned how to find the magnitude of a vector, about equal vectors, about negative vectors. So students, here are some links which will provide you with additional information regarding today's lesson. So take note. The first link, the second one, and the third link. So students, this video on vectors and translation ends here. Remember that this program was the second part of the chapter on vectors and translation. In the first part, we talked about vectors, scalars, and how to express a vector in column form. Today, you have learned about magnitude of a vector, equal and negative vectors. In the next video, we're going to talk about translation. So friends, till we meet again, it's a goodbye and see you soon.